Okay, started. Started. Not for children. It's funny that we have to mark every time that the content of the conference is not for kids. You have to keep kids away from the computer graphics. That's relevant. Okay, Marco Potenziani, the video should be ready for being embedded in the web page.
Okay, thanks, Marco.
Hi Andrea.
Ciao.
Ciao, grazie.
Posso anticipare il treno.
Saremo puntuali.
So the first three papers are long paper, and then the final one is a short paper.
I was trying to show my 3D in a cool HTML. Turned out was not that easy. It didn't work so well. So I tried browsing around. For an answer took so long. Till I found this orange website where I heard singing this song. WEB3D is the place to be. Here your scene will not freeze, it will show like a breeze you will see. WEB3D, you can join for free. Thanks Chronos and Ivy, and you can log in and then leave. WEB3D is in Italy, with the soul and the mare, the best of mangiare virtually. Don't be mad, don't cry and be sad. You will follow our runs, dress code underpants. Now picture that at WEB3D. It's so fun to be, and the social event and takes your tower that's bent, you see. WEB3D is in Italy. I hope you enjoy. Good luck and then fun virtually.
Hello, Carlos. I promoted you as panelist.
Okay. Can I start, or do we have to wait for a few minutes?
Okay, good morning again. We're about to start. We are starting now. Welcome Andrea Giacchetti. Hi, Andrea.
Hi.
And he will be the session chair of this morning. So I'll leave the floor to you, and we can start, I believe, with the first paper.
Okay, thank you, Fabio. And I'm very happy to be here to be the chair of this first session of WEB3D. We have 4 very interesting papers, very heterogeneous and very interesting papers. And I think that it can be very interesting to listen about them. And so we can start with the first one. The first one is Solid and Effective Upper Limb Segmentation in Egocentric Vision by Monica Grosso, Nicola Capece, and Ugo Erra from University of Basilicata Potenza. So we can start with the presentation, and then we will have Monica for the question and answers.
Can you all see the video?
Yes.
Yes.
Hi everyone, my name is Monica Grusso, and today I will present to you our work, Solid and Effective Upper Limb Segmentation in Egocentric Vision. After a brief introduction and related work, I will discuss the construction of our dataset and the proposed approach. I will show you some of our results, and finally I will summarize conclusion and future work. Recently, deep learning-powered web solutions have been increasingly developed, and several in-browser frameworks were designed that allow users to perform network inference and training directly in the browser. In this example, I train a small network for digits and written classification. On the right, you can see the plots for monitoring the loss and accuracy during training. And at the end of the training, I test my network in the browser. In this example, I collect a dataset consisting of different images, several images showing rock, paper, and scissor for image classification. I design a convolutional network and train it in the browser. And at the end of the training, I test my network using images captured using a webcam. This is an example of face landmark detection using a deep network and perform inference in the browser. This is my last example and shows end tracking in the browser. The most common web applications are online virtual reality chat rooms that allow users to see each other and share contents. This is an example in the figure that shows Mozilla Hub's environment. Users are usually represented with a virtual avatar. Another example is a 3D collaboration platform on the right, where the users can interact with the virtual object using their controllers that are also visualized in the virtual scene. Web-based solution can provide a virtual environment that runs directly in the browser, and so results in an easy setup and cross-platform portability. With the widespread availability of wearable RGB cameras and end-mounted displays, systems for analyzing and detecting ants in a first-person perspective called egocentric vision or egocentric viewpoint have been designed. In this figure, you can see user ants tracked using a lip motion controller and visualized in the virtual scene using a virtual ant. The question is, can the user be more involved in the virtual reality and web-based virtual environments, seeing their real ants and limbs in the virtual scene? We designed and proposed a deep learning approach for upper limb segmentation in an egocentric vision. It can allow locating the user limbs interactively and obtain accurate information at pixel level. That may increase the user's sense of presence and body ownership, for example, in WEB3D virtual environments, providing a general-purpose solution that can be executed on any device using a web browser and without a specific hardware configuration or software installation. In these images are shows on the first line the inputs, and on the last line our segmentation output overlaid on the input images. There are several works on hand and arm segmentation. The most part of them focused on hands up to the wrist or bare arm. One of the first focused on left and right and identification and segmentation. And the most recent was proposed by Gonzalez et al. They train a deep neural network for hand and arm segmentation. That network was trained using their own semi-synthetic egocentric arm dataset that consists of more than 10,000 composited images. Although their model achieved really interesting results, several false positive and segmentation errors in color similarities between background and foreground were found. Since obtaining ground truth segmentation mask is very labor-intensive, time-consuming, and sometimes impractical, synthetic and semi-synthetic datasets were proposed, have been widely collected, and they allowed to get labels quickly and with little effort. As you can see on the left, synthetic end are produced in a completely artificial manner, and often they look unrealistic, and semi-synthetic dataset combines real and computer-generated components. Both approximate real data. In the case on the right, semi-synthetic data were obtained from the EGO-ARM dataset, and we found several errors in the foreground that was extracting using a green screen. As you can see, often the ends looks green due to foreground extraction from the green screen setup, and different images were used as background. Often they are low resolution, and the composited images look really unrealistic and artificial. Often several computer vision techniques are needed to bring realism to those data, and for this reason we focused on real dataset, analyzing existing datasets such as this data, and we found some errors in the annotations in this case, or polygonal masks. In the case of Ego YouTube ends, we found only labels for the ends up to the wrist, and since we were interested in the ends and arms, we discarded this data. In other cases, only bare arms were labeled and clothes were not labeled, and there were some errors in the annotations and so on. So we collected a large dataset, real dataset, that overcomes the limitation of existing dataset. In the case of WEB3D and deep learning approaches, recently some works were proposed. In particular, the first two introduced models for model shape estimation, and the last one proposed a conditional generative adversarial network (GAN) for global illumination maps generation of 3D human organs. They used TensorFlow.js for network prediction in the browser, which is a deep learning frameworks that allow network training and prediction in the browser. Our dataset consists of about 46,000 well-labeled real-life images that includes the best data from EDSH and TIGO dataset. We investigated the quality of this data to select the best data of both images and labels, discarded the worst data, such as errors in labels. We selected images in egocentric vision with different skin tone, as you can see, different tones, different lighting conditions, scenarios, in the case of motion blur, occlusions with object and with interend occlusion, and we collected our dataset called EgoCam that allows increasing the number of data in our dataset, introducing also female limbs with different clothes, and capturing also the elbow and the upper arms, because existing dataset focused only on hands and the first part of the arm. But in the case you use a camera with a wider field of view, this camera captures also elbow and the upper arm. So since the collected dataset had different orientation and aspect ratio, we designed an automatic procedure for square cropping. At the end of the cropping, we inspected all the saved images and deleted the unuseless clipping, such as with no ends or no arms. The proposed approach is based on convolutional neural networks that are feed-forward neural networks designed to process data in a multidimensional, provided as multidimensional arrays, such as images. The main advantage consists of a huge reduction in the amount of parameters and invariance to input translation compared to standard feed-forward fully connected networks. This kind of network is composed of a first part responsible for feature extraction from low-level to high-level features such as line, edges, and then objects such as recognizing the tail or the mouth. And the last part of the network is built with fully connected layers, and in this case performs classification. Contrary to a common feed-forward neural networks, as shown on the left, where each neuron in a layer is connected to all neurons in the subsequent layers, CNN neurons are arranged in 3 dimensions with height and depth. The core block is the convolutional layers, which perform convolutions, where each neuron is connected only to a local region in the input spatially, but to the full depth. Each hidden neuron share the same weights and bias on its connection, and for this reason all neurons in the first hidden layer, convolutional layer, can detect the same feature but in different location of the input image. The convolution is performed between 2 volumes, the input volume and the convolutional kernel, which consists of 1 or more filters, and the values of those filters is learned automatically during training. Although it is essential to specify some hyperparameters such as the filter size or the stride, which is hyperparameters that control the moving of the filters on the image. Another type of convolution is called authors or dilated convolution, which upsample convolutional filters with holes, defining a spacing between the values in the kernel controlled by an hyperparameter called authors rate. In this example, a 3x3 kernel is dilated with a rate of 2. The goal is to obtain a wider field of view that takes the context more into account, but without increasing the computational cost and the number of parameters. This is really useful in the case of real-time segmentation. Since convolution are linear operation, usually a nonlinear activation function is used after convolution. The ReLU is the most used nonlinear activation that allows a faster and effective training of deep networks on large and complex dataset. It is efficient, especially in image-related tasks. After convolution, usually is placed a pooling layer, which performs pooling operations such as max pooling or average pooling, which is applied to each feature map independently, contrary to convolution, and performs downsampling along the spatial dimensions, with a huge reduction in the number of parameters and ensuring translation invariance. We designed a deep learning approach based on the DeepLab V3 Plus architecture, which is a deep CNN with an encoder-decoder structure. The encoder extracts semantic information and reduces the size of the feature map, while the decoder recovers spatial dimensions and detailed object boundary information. We train different networks, changing the backbone network. In particular, we test ResNet with 50 layers, 101 layers, Exception with 41 and 61 layers respectively. The encoder is composed of a backbone network, an ASPP module, a one-time-one convolution or point-wise convolution, while the decoder performs bilinear upsampling and convolution to upsample the feature map. The heterospatial pyramid pooling module allows capturing the multiscale context effectively and improve segmentation. It consists of several layers in parallel, a convolution, a pointwise convolution, 3 authors convolution, and an image pooling. We train our models using a GPU, performing the augmentation. We use the cross-entropy loss function, which is a well-known loss function for segmentation tasks, and SGDM, stochastic gradient descent optimization algorithm, with a polynomial learning rate with the power value 0.9 and momentum 0.9. All networks using pre-training weights. The first 3 cases, ImageNet, which is a large-scale dataset for image classification and object detection. The last one, pre-trained weight on ImageNet and the COCO dataset. COCO dataset is a smaller dataset, but used also for segmentation. We performed a first test using our test set, a quantitative comparison using well-known metrics shown in percentage, accuracy, intersection over union, and mean F1 score. In the case of the overall evaluation, we performed an average over classes, and in the case of classes, we used accuracy, intersection over union, and mean F1 score. The obtained values show excellent results for all training networks. The worst model diverges by a limited quantity, 1 or 2%, respect to the best model. So we spec'd the mask obtained, and we noted that several small errors can be found. And in conclusion, it was not so easy to identify the best network observing those results on our test set. Then we performed another test using Ego Gesture Seg, which is a subset of the well-known Ego Gesture dataset, which was labeled by Gonzalez et al. It consists of challenging scenarios and situations, and we conducted this experiment to assess the generalization level and highlight the differences between the performances of the training models. As you can see, the best model was the last one with exception 65 backbone network, and there is a significant difference compared to the other models. Then we performed a qualitative analysis. Those are some of the images of Ego Gesture Seg dataset and the output obtained. As you can see, the network with exception 65 backbone found the limbs in all images with only minor errors in the third case. And it was the only model that did not make classification error related to the background in the last image. Okay, these are really challenging with strong lighting, dark limbs, and a huge amount of motion blur. In our opinion, the results obtained with the Ego Gesture Seg dataset prove that using initial weights pre-training on both ImageNet and COCO dataset can help the network to have a broader view and be able to generalize better in this case. And furthermore, the conducted tests show that the exception-based architecture is more robust to challenging situation than the ResNet one. We compute the average inference time using the GPU and testing our RGB images, and all models prove more than real-time performances. Those are some results on videos which were obtained using the best model, exception 65 as backbone network. The colored segmentation output mask were overlaid on the input frames. This is a really challenging situation in which you can see a watch with the reflective surface, and in this case a small reflective metal ring on the user end and on the user finger. There are also some errors, but impressive results were achieved in all these cases, also in the case of cloth. In conclusion, we proposed a robust deep learning approach for upper limb segmentation from an egocentric vision in unconstrained real-life environments. Our network proved to be robust to both bare and clothed human upper limbs. We obtained good results and promising results in the case of inter-end and end-to-object occlusion, in the case of variable lighting condition, skin colors, indoor and outdoor real-life environments. We collected a large comprehensive dataset to train our network and tested several configurations to find the best model for this task. It could allow users to see their own limbs in the virtual 3D virtual environments, and interact with virtual objects using their own hands instead of virtual avatar, improving the user sense of presence and embodiment in virtual environments, and providing a general purpose solution that can be executed on any device using a web browser. In the future, we plan to conduct a user study to assess the usefulness of our approach in web-based immersive application and perform a comparison with state-of-the-art methods for egocentric hand and arm segmentation. Thank you for your attention.
Okay, thank you very much. And I think we can start with a quick question and answer session. I ask if are there questions from the audience. In the meanwhile, Monica, are you there?
Yes.
Okay.
Hi.
If there are no questions for the audience, I have some questions. Too many, probably. It's a very interesting work because I think. Okay, I see that there is a question from the audience. Dan Brutzman asks if he wonders if there is a metadata vocabulary available that describes gestures. But I think that the gestures are...
We were not interested in gestures,
yes.
But also only in segmentation of hands in any pose.
Okay, so I come to my question. Yes, I see that
You're
you are
welcome.
in segmentation, and actually it's quite important to have high quality data sets, annotated data sets for segmentation tasks, of course. But I was wondering first, because you presented at the beginning the idea of using these tools in WEB3D applications, and you showed real-time performances, but I was wondering if you can get these performances on a mobile device using a web architecture, because I think that if you need to have a real-time hand and segmentation for visualization purposes, there is a very strong requirement regarding to the low latency of the overall system.
Thanks for your question. Yes, probably we did not have real-time performance on mobile, since DeepLab, the core architecture, is not lightweight model for mobile. But in future, we can change network or perform some modification to the network, to the core network, for example, using the mobile net core block to allow real-time performance on mobile.
Yes, because I think it is important.
Yes.
Did you check if the segmentation of the hands performed with your method? Did you plan, of course? You said that you're not interested in gestures, but one thing that one can wonder if it can be used full to have this segmentation to improve the performances of hand pose algorithms, because this can be interesting for interaction in virtual reality.
Yes, segmentation can be used as pre-processing step for hand tracking and pose. Yes, of course, to remove background and so allow better performance.
You did not test.
No, in future.
Can be
future work.
Okay. Thanks. Let's see if
Thank you
there
for your
are
question.
any other questions. Okay. Carlos Andujar says a nice extension would be to extract also the unspose. So of course we have talked about this. Okay.
Yes.
Any other questions? Okay. If not, thank you very much, Monica.
Thank you.
We can move to the second presentation. Thanks again.
Thank you so much.
And we can move to the second presentation, that is interactive volumetric region growing for brain tumor segmentation on MRI using WebGL, and by Jonas Kort, Paul Brackmann, Daniel Limberger, and Christoph Lippert from the University of Potsdam in Germany. And let's see the video, and then we will have Jonas for question and answers.
Hello everyone, I'm Jonas and I will present our work on interactive volumetric region growing for MRI scans in WebGL today. Before I get to that, I quickly want to say a couple of words about myself and the other involved authors. My name is Jonas Kort and I'm a graduate student at the Hasso-Plattner Institute of the University of Potsdam. There, my co-author Paul Brachmann and I are part of a team working on an image segmentation suite for volumetric medical images called Vision. The workflow we present in our paper is part of that work and integrated into Vision. We were supported by Daniel Limberger, who's a PhD student at HBI, and Professor Dr. Christoph Lippert, who's a professor for digital health and machine learning at HBI. While our workflow is universally applicable for any volumetric MRI or CT scan, we focus on brain tumor segmentation. To segment such a brain tumor, one typically looks at an MRI scan one slice at a time. Here we can see one single slice of such a scan. A typical resolution used for brain MRI is 1 voxel per millimeter. This means that for the typical head size, you get around 200 voxels in the X, Y, and Z directions respectively. This particular scan has 155 slices with a resolution of 240 by 240 each. Also, when looking at this example, we can probably all tell that this brain is not healthy. Since brains are usually rather symmetrical, something has to be wrong here. And in fact, the brighter shades of gray in the bottom right corner correspond to the high water content of a brain tumor. In a clinical setting or for studies, it is often necessary to segment out exactly the voxels which are part of the tumor. In clinical practice, for example, tumor segmentations are necessary to conduct risk assessments before brain tumor resection operations. For such risk assessments, one important factor is the minimal distance between the tumor and important motor nerves in the brain. If the tumor is too close to those nerves, it would be very likely that they would get damaged during an operation, which could result in the patient being unable to speak or walk afterwards. But to precisely measure the distance next to the location of the motor nerves, a full tumor segmentation is necessary. Similarly, the tumor segmentation can be used to monitor the tumor volume in a time series, both for large data sets in research studies or for individuals, patients in a clinic. Segmenting such a tumor looks like an easy task here because we're just seeing one single slice of the scan. In reality, it's a time-consuming and expensive process because a trained radiologist has to go through every single slice of the scan and precisely color the voxels which are part of the tumor. The result is a volumetric segmentation, which, as you can see here, we can also render in 3D in order to give researchers and clinicians a way to see the whole segmentation at once. We use direct volume rendering with ray marching for this view, and in order to run this on any device, including tablets with minimal compatibility issues, we rely on WEB3D technology. In particular, we use WebGL with 3JS for both the 2D segmentation editor and this 3D view. However, because creating such volumetric segmentations is a big effort, of course, the ultimate goal is to fully automate this, probably using deep neural networks. The main bottleneck of such neural networks is that they rely on a vast amount of training data which has to be segmented by experts. To streamline this training data segmentation process, semi-automatic segmentation tools are necessary. Different approaches for this exist, but we focus on region growing based approaches. This means that the user places a seed which then grows into a larger region of voxels with similar intensities. However, without knowledge about the structure the user intends to segment, region growing algorithms tend to overgrow the intended region by a large amount. This is why region growing tools in a typical 2D slice-based view are usually limited to segmenting one single slice at a time, enabling the user to judge the correctness of the grown region accurately at a glance. To enable confident and atomic segmentation of a whole 3D volume, we thus use a combination of the standard two-dimensional slice-based rendering and the three-dimensional direct volume rendering. This helps users to recognize large overgrown areas quickly, even for volumetric grown regions. Additionally, we do not force the user to discard the whole grown region in case of an error. Instead, we provide them with a preview that they can interactively tune to scale back how far the region may grow from the seed. This way it is possible to limit the grown region in a way that it cannot escape the intended bounds while still keeping as much as possible of the desired segmentation. The specific workflow of our volumetric region growing tool begins with the user selecting a threshold used for region growing. This threshold controls the maximum difference in intensities between neighboring voxels, which still allows the region to grow. In the second step, the user places the seed. This can be done in both the 2D and the 3D view. In the 2D view, the user can scroll through the different slices and select their seed using their mouse cursor. In the 3D view, the user can click anywhere in the rendered image, and the seed will be placed at the first high opacity intersection of their click with the volume. This works especially well in the cone transfer function shown here. This transfer function works by clipping away a cone from the rendered MRI intensities while not clipping away the rendered segmentations. This way it is possible for the user to look into and place a seed in the middle of the brain while still seeing any pre-existing parts of the segmentation like the teal one shown here. After the seed is placed, the region growing is executed. The grown region is shown as a preview in a distinctive color, in this case the dark blue, to differentiate it from any pre-existing parts of the segmentation. Additionally, a tuning UI panel is opened, giving the user access to a slider that controls how far the region may grow from the seed. This lower image series shows the effect of using that slider from within the 3D view. Next, in the fourth step, the user can then freely switch between the 2D and 3D views while manipulating the slider to control how far the region may grow from the seed. This way it is possible for them to limit the segmentation in a way that it cannot escape the intended bounds. As guidance, different transfer functions can be used. The one shown here renders the prominent edges of the underlying MRI, which can be useful to judge whether the region has escaped the intended bounds. Finally, in the fifth step, the previewed region is merged into the existing segmentation to finish the process. Now that I've explained the workflow, let's get straight into a demo. This is Vision's user interface. From here we can import a scan by simply dropping it into the workspace. In this case, we are loading a FLAIR series from the BREDS 2018 dataset. This particular imaging modality already makes the tumor contained in this scan brightly visible. Our task will now be to generate a segmentation mask for it. While previously in Vision we had a 2D smart brush that uses region growing on a single slice, this still forces us to go through potentially many slices and can also lead to segmentations that do not produce objects with smooth surfaces in 3D. These issues can be alleviated at least in part by our 3D region growing workflow. It can be triggered by selecting the 3D Smart Brush tool. We may then choose a fitting region growing threshold. For tumors like this one, we found a value of around 40 for the maximum allowed difference for region growing to be suitable. Next, we can select a seed by clicking on a voxel in the tumor. Vision then performs the 3D region growing and we are presented with a preview of the resulting segmentation. If we are not happy with the seed location, we can click again to find a better one. Currently, this preview shows us the maximum expansion of the grown region. However, using the tuning slider, we can tweak how many steps the region growing should be allowed to grow. It becomes apparent that judging this expansion in 2D alone does not give us the full picture. This is where our direct volume rendering approach comes in. When switching to the 3D view, the whole segmentation can be judged in the context of the original scan. This is facilitated by a transfer function that is based on the underlying scan's gradient. Here we can see that the region overgrew significantly in this particular part of the image. So we can use the tuning slider to dial it back a bit. Once we're happy with it, we can accept the grown segmentation. At this point, it becomes part of an annotation layer that can, for example, be exported for statistical analysis. The power of this layer concept is that we can segment multiple structures on the same scan and visualize them together. Additionally, we can make use of the multimodal imaging to generate more accurate segmentations. Let's import the T1 weighted series for this patient as well and add a new layer to segment out the lateral ventricles, which are these fluid-filled chambers in the center of the scan. Bear in mind, I'm no medical expert, so this segmentation is only going to get as good as my limited anatomical understanding. This time, let's set the seed right from the 3D view. To do this, we can either use a clipping plane tool, or the cone cut transfer function that allows us to see into the scan. As seen previously, we can now tune the allowed growth of the region. To judge this more accurately, we can switch back and forth between the 2D and 3D view. Once we're happy with the shape of the segmentation, we can accept it as before. It is now part of the second annotation layer. As you can see, the segmentations are still not perfect. Due to the way region growing works, they tend to contain small holes where outlier voxels occur. To close these, Vision has a dilate erode tool that can fill small holes by first iteratively dilating a segmentation and then eroding it the same number of times. If further adjustments for even more precise annotations are needed, 2D brushes can now be used for manual touch-up. You may have noticed that the resolution in the 3D view dropped while moving the camera. This happens due to our progressive rendering implementation that ensures smooth frame rates even on consumer-grade hardware. This effect can be pronounced even further if we switch the view quality to low. A second progressive feature of our rendering is that of asynchronous lighting computation. As you can see, with the cone transfer function, the scan appears rather dull and contour-free while moving the camera. However, as soon as we stop, a first local ambient occlusion path is computed in the background and used to re-render the image as soon as it is ready. From there, the ambient occlusion quality is progressively refined. Finally, we want to mention that our workflow also supports virtual reality. And while this might not be suitable as the default mode of working, the enhanced sense of depth it offers, from our experience, helps to better judge the spatial structure of generated segmentations. Now that you've seen our workflow in action, I want to get into some of the implementation details. The region growing algorithm itself is rather simple. We wanted to keep it this simple to minimize potential biases when training a machine learning model with the resulting segmentations. A voxel can become part of the region if one of its 6 neighboring voxels is also part of the region and the intensity difference between the 2 voxels is smaller or equal to the user-defined threshold. Additionally, it's also required that the intensity difference with the initial seed voxel is smaller than 1.5 times the user-defined threshold. This makes sure that the region can't grow too far in case there is a smooth intensity gradient between 2 entirely different areas of the scan. Next, let's take a look at the data flow behind the whole process. The process is initiated by the user selecting a seed voxel. Based on this, an initial segmentation is created containing only that singular voxel, and the seed value is extracted from the underlying scan. In the growing phase, that initial segmentation can then iteratively grow based on the extracted seed value, the underlying scan, and the user-defined threshold. During this iterative growing phase, we use two frame buffers as alternative inputs and outputs to render back and forth between. In each rendering step, the region can grow by one voxel in each direction. The resulting segmentation is visualized as a preview together with the original segmentation and can be interactively tuned by the user to limit how far the region may grow from the seed. To achieve interactive frame rates during this tuning process, we don't only store which voxels are part of the region, but also in which step they became part of the region. As we have 1 byte of space for this and need one value each for the voxels not part of the region and the voxel part of the seed, we end up with 254 region growing steps. During the tuning process, we can then simply threshold against this value instead of having to recompute the whole region growing again. Once the user is happy with the previewed segmentation, it is added to the original segmentation to form the merged segmentation. To allow the user to pick a seed in the 3D view, we use a volumetric picking shader. The result of rendering the whole volume using this shader is shown here on the right. In reality, however, we only need to render the one single pixel that the user actually clicked. This volumetric picking shader performs the same front-to-back ray marching and color accumulation as the normal volume shader. However, when a small opacity threshold is reached, the ray marching loop is terminated and the current normalized volume coordinates from the ray marching process are rendered into the R, G, and B channels of the output buffer. To indicate that a target was hit, a 1 is rendered into the alpha channel. In case no high opacity is reached during the ray marching process, which means that the user clicked onto the background, a 0 is rendered into the alpha channel. If a target was hit, the rendered normalized volume coordinates are converted into voxel coordinates, which are then used as the seed for region growing. I would now like to invite you to try everything I just explained and show to you yourself. Vision is available online at vision.org and includes the volumetric region growing tool. Sadly, because of data privacy reasons, we cannot share a scan with you that you can simply import. However, if you have a scan of yourself, feel free to import it. Any data that you import will stay on your device and will never be sent to our servers. In case you don't have a scan laying around, you can find open access scans on the internet. With that, I would like to thank you for your attention, and of course, we're open to discuss any questions or suggestions that you might have.
Okay, thank you very much. Jonas is ready. Are there questions from the audience? Okay, one.
Yeah, I was curious. The thing about ambient occlusion, I have seen that really increased the legibility of the dataset. However, ambient occlusion maps on the same grayscale as the density. So have you asked the medical people if this may interfere with the perception of the density data?
That's a good question. I don't think we've parsed, but yeah, you're right. It does map on the same grayscale, and but I mean the difference in grayscale is not that big, so I'm guessing it's not a big problem. But it's a good question.
Because it's a problem that also we had many times, because well, you have your 3D model with color, and then you put some ambient or some shading enhancement to make it more legible, and then you lose the actual value that was measured. So I know there's these conflicting needs, and I don't have a solution, but I just wonder if you had some insight on this aspect. Thank you.
Yeah, I mean, we don't have a perfect solution either, I guess, but we do allow the user to turn off the shading, and we also have we didn't show this, but we also have phone shading, so you can. I mean, we get the gradient from the scan, so we can shade it with phone, but that kind of adds specular reflection again, which also is the same grayscale again, so it's not really a solution to the problem, but we do allow the user to turn off the shading if they need to see the values. But I think like the real solution is to combine the 3D and 2D view here and have the user be able to switch to the 2D view, and there we actually allow them to look at when they hover a voxel, we show them the exact measured value, and so they have perfect access to it.
Oh, that's interesting. Yeah, it could be. Thank you very much.
Okay. Any other questions? Okay. Meanwhile, I have some questions. So there is another question from Donna Brutzman. Did collaboration of the web help improve visualization insights?
I don't completely understand the question. So because it's not a collaborative app at the moment.
So I think that it is an answer. If it is not a collaborative web tool, it doesn't improve. I was wondering, okay, did you develop this tool as for medical doctors asking this kind of tool for creating quickly annotations? I understand correctly.
Yeah, so the goal is to quickly create training data to then train deep learning.
Because I was wondering, because actually region grow is really a very basic segmentation algorithm, because it is difficult with the simple thresholding and region growing to have a starting point for correcting manually the segmentation that easy to correct, because you will obtain a lot of leakings of regions, all and so on. And of course, there are many better algorithms for segmentation that are typically used for automatic segmentation, not involving neural networks. You can use graph cut or level sets. Why did you compare that? Why did you did not choose slightly more complex algorithms for segmentation, or did you find that for your task region growing was enough?
So specifically for brain tumor segmentation, region growing was already enough. I mean, you saw in the demo that the brain tumor was segmented quite well. And it really depends on the use case, actually. So we found that for larger things like brain tumors and for the ventricles that we also showed, the region growing is already enough, because they have kind of sharp borders, but you also saw that it can escape. So that's why we implemented this slider where you can tune the preview and you don't have to completely start over again. But yeah, for other parts that you might want to segment, region growing might not be the best option. And then we do plan to explore other algorithms in the future and compare them to region growing.
Okay, thank you. Other questions? No more questions. So thank you very much again, Jonas. And I think we can move to the next presentation. Okay, the next presentation is a platform for developing and fine-tuning inclusive 3D navigation techniques for the immersive web. And sorry. So we have to find the paper just to look at it. okay, by Ahmed Kamal and Carlos Andujar from Universitat Politècnica de Catalunya. So we can start the presentation, and then I think Carlos will be ready for discussion.
Hello everyone, my name is Carlos Andújar from Birbic UPC in Barcelona, and today I'm going to present this work, which is about the creation and optimization of navigation techniques for the immersive web. This paper is a joint work with Ahmed Kamal, who implemented this platform as part of his master thesis. Let me start with a quick overview. Navigation is one of the major user tasks when interacting with virtual environments. And although hundreds of interaction techniques have been proposed to navigate through 3D scenes, 3D navigation still poses a high entry barrier for many users. Virtual reality devices allow for a more immersive exploration of 3D worlds, but navigation in VR is challenging for many users due to potential usability issues related, for example, with specific controllers, user skills, and motion sickness. In this paper, we discussed the design of a test platform to facilitate the creation and fine-tuning of navigation techniques for the immersive web. The key idea is that we provide ready-to-use versions of the most common navigation metaphors like walking, flying, and teleportation, and we allow users to customize every single aspect of these techniques to the point of being able to specify the exact mapping between user actions and virtual locomotion. We will show that this method facilitates the adaptation of navigation techniques to specific people, scenes, and applications. First of all, why should we care about navigation for the immersive web? In the last few years, we have seen a substantial evolution of the different technologies that allow people to experience 3D virtual environments. Thanks to the advances in laser scanning and photogrammetry, the digitization of objects, buildings, and sites has become a common practice in many fields, such as cultural heritage. The web is the ideal platform for the dissemination of these 3D models. Since the web is open and based on well-defined standards, anyone can publish content, which in turn can be accessed by anyone. Furthermore, web browsers exist for many platforms, including computers, tablets, smartphones, TVs, and even VR headsets. Actually, VR headsets are the focus of this work. Many VR devices today are supported by the WebXR Device API, which provides a platform-independent way for accessing these VR and AR devices. So as I mentioned, 3D navigation is an essential task when interacting with 3D scenes, and usually the first thing we do when we open a 3D scene is to navigate. So is 3D navigation an already solved problem? Well, I don't think so, although there are some cases where navigation is easier than other cases. On the one hand, navigation difficulty depends on the type of a scene. When the 3D scene is just a single object, navigation is easier, and it can be accomplished with just rotate, zoom, and pan interactions. But when the 3D scene is more complex, for example, a building, navigation is harder. Users can become disoriented and fail to explore the parts of the scene they are interested in. On the other hand, navigation also depends on the platform, being completely different for non-immersive devices and virtual reality devices. For virtual reality devices, the navigation technique plays an essential role in the user experience. On the positive side, room size tracking allows users to inspect the scene by just walking, and that's the most natural option, but of course it is limited to a small scale exploration, let's say up to a few meters. For medium and large scale exploration, we need a proper navigation technique. On the negative side, in VR, every single application has its own navigation technique. There are a few navigation metaphors, for example, teleportation and flying, but the actual implementation of each metaphor is unique for every game if you consider all the details and specifically which user input is considered and how this input is mapped onto user movement with respect to the 3D world. Actually, interaction techniques for 3D navigation have received a lot of attention. A recent study has identified and characterized over 100 navigation techniques used in virtual reality. The reason for such an increasing variety of navigation techniques is twofold. On the one hand, VR software and hardware are in constant evolution, opening new opportunities for 3D interaction, for example based on eye tracking and hand tracking. On the other hand, current interaction techniques for navigation have important limitations, which bring us to another key factor for navigation difficulty, which is the user. I mean, user skills, experience with 3D and VR, and motor capabilities. Actually, some works have pointed out that there is an inherent trade-off between accessibility and simulation sickness. In other words, if the navigation technique mimics real-world movement, you minimize motion sickness, but you make your application less accessible to people with limited mobility. Conversely, if the navigation technique departs from real-world movement and embraces a more abstract mapping, for example just pointing or looking, then we increase accessibility, but we also create discrepancies between visual and vestibular stimuli, which might result in user discomfort and motion sickness. So we can conclude that no universal technique for VR navigation exists that works well for all situations. As we have seen, the suitability of a specific navigation technique depends on many factors, for example, the virtual environment, the target platform, and the user profile. We believe that there is an increasing need for more exploratory studies of VR navigation techniques and more mechanisms to facilitate the adaptation of existing techniques to specific hardware, environments, and users. For example, those users for which VR navigation poses a high entry barrier, people with no experience in 3D or VR navigation or with motion disabilities. So what's our contribution? We present a method to facilitate the creation, adaptation, and fine-tuning of interaction techniques following the major navigation metaphors, I mean teleportation, flying, and walking. At the core of these interaction techniques is the mapping of user input onto user motion, although other components also play an important role for the user experience, for example, the addition of techniques for alleviating motion sickness. We will describe our experience with a web platform using JavaScript, WebXR, and 3GS for adapting interaction techniques based on these navigation metaphors. In particular, we designed the platform to support easy experimentation with interaction techniques for navigation, where developers can easily create and test new mappings through user-defined custom functions, easy customization to particular 3D scenarios, and similarly, we wish to facilitate the adaptation to people with no experience on 3D navigation, for example, art historians willing to explore a virtual museum. Let us quickly review the previous work on VR navigation. Virtual locomotion techniques can be roughly classified into walking-based, steering-based, and selection-based techniques. Walking-based techniques, such as walking in place, mimic the natural ways of moving around. These techniques include real walking as well as other techniques involving repetitive motor actions such as arm swinging. Steering-based techniques provide a continuous control of direction, which can be controlled using the user's body, for example gaze, hand, torso orientation, or through physical steering props. Selection-based techniques greatly simplify navigation by letting users focus on where to get instead of how to get to a specific location. A widely known selection-based technique is teleportation, which moves the user to the chosen destination either instantly or gradually. A proper design of the navigation technique could be the difference between enjoying the presence of being in another world or suffering discomfort, disorientation, and nausea. Common methods for alleviating motion sickness include field of view reduction and independent visual background. Some techniques such as instant teleportation lack optical flow and thus are unlikely to trigger motion sickness. Turning to our approach, we propose a tool to facilitate the design, testing, and fine-tuning of navigation techniques for virtual reality. Our tool is based on the following premises. First, we believe that adapting the navigation technique to a specific scenario can improve the user experience. For example, a narrow cave in a factory might require completely different navigation techniques. We also think that adapting the navigation technique to specific user profiles, for example, art historians, or functional abilities of the users, can make the application more inclusive. And fine-tuning the different parameters and design options that define a navigation technique can make a large difference. Very often the devil is in the details, and a poor choice of some parameter can make a navigation technique usable in some specific scenarios but unusable for the rest. Finally, all these adaptations are effective if they can be implemented and tested in an easy way, with nearly immediate iteration cycles, with a complete control of the mapping between user input and locomotion changes, and with arbitrary runtime modifications. We support two different levels at which designers can customize a navigation technique. First, parameter level adaptation. The designer chooses a specific navigation technique, for example, continuous steering, and simply modifies predefined parameters, such as the speed. The designer can also specify non-numerical choices, for example, which button must be used to navigate, but available choices are predefined. The second level is user-defined adaptation. In this case, the designer also chooses one of the predefined metaphors and provides the source code defining the mapping between user input and locomotion output. Therefore, designers are completely free to specify the mapping with the only limits imposed by the selected metaphor. Our current prototype supports three major navigation metaphors: free teleportation, teleportation with predefined targets, and flying or walking through continuous steering. Let me describe the basic behavior of these metaphors. In free target teleportation, the user points at any target location and the application automatically moves the viewpoint to that target location. The teleportation points metaphor is similar to free target teleportation, but target locations are limited to a predefined collection of targets. Finally, the walking-flying metaphors allow users to walk, grounded navigation, or fly with no high constraints through the virtual environment using a continuous steering technique. A key issue for fast experimentation is to allow users and interaction designers to quickly change these parameters through a graphical user interface. Our prototype includes two different UIs. The 2D UI is available anytime the application is not in VR mode and can be interacted with traditional interaction devices, for example, mouse and keyboard on a desktop PC. Conversely, the VR UI is available only when the browser is in VR mode. Thanks to the WebXR emulator, designers can test immediately any adaptation by just switching into VR mode. So users are not required to put the VR headset on and off every time they modify some parameter. Let me discuss in more detail how users can adapt any technique by just modifying the parameters. I will discuss only free teleportation. The options that can be adjusted were decided taking into account well-established analysis on the different subtasks involved in selection-based techniques. We now briefly describe the different options. The first group is concerned with the target selection part. Starting pointing refers to which user input initiates the selection and causes the selection ray and/or the selection target to be shown. Available choices include, for example, specific buttons of the controllers, as well as an always active option. Pointing direction specifies how to compute the base pointing direction, and available choices include the controller's forward direction, the user's head, and the user's torso. Concerning the maximum distance to teleportation, we allow the user to limit the maximum distance for selectable target positions. This is especially suitable for curved rays. Ray type refers to whether to use a straight line segment or a curved selection ray. Curved rays provide a more equally spaced mapping between ray orientations and target distances. Confirmation refers to which user input confirms the target selection. Available options are similar to those for start pointing. The second group of options refer to the actual teleportation part, as well as field of view reduction to reduce motion sickness. Teleportation speed is the camera speed towards the target, or 0 for instant teleportation. Field of view reduction fade-in is the time, usually a few milliseconds, to gradually reduce the field of view. Similarly, the field of view reduction type is how much the normal field of view must be reduced during gradual teleportation. Finally, we allow users and developers to define programmatically their own mappings between user actions and navigation control. The user is free to provide JavaScript code for a collection of functions defining all aspects of the navigation technique. In this example, we are providing our own expression to compute the teleportation speed. Again, we can test immediately the resulting behavior in VR mode. This seems to be quite slow, so we are going to modify the expression to speed up the motion and test again. One can argue that developers and user interface designers can write these pieces of code just as part of their JavaScript modules. However, our application allows these functions to be written directly on specific user interface components. Furthermore, the functions can be edited at any time and are evaluated at runtime. For example, we can navigate to a specific room and test different mappings immediately without reloading the application. This method makes testing iteration cycles much shorter and thus allows for a more comprehensive testing of different mappings in varied situations. Let me describe the kind of custom functions experimenters might provide to define precisely the behavior of teleportation. We indicate the expected JavaScript return type within parentheses. Unless otherwise stated, these functions are invoked automatically every frame. Starting pointing returns a Boolean value. The target indication will be initiated as soon as this function returns true. The pointing direction returns a 3D vector. This is the function providing the 3D vector to be used as pointing direction. Confirmation should return a Boolean value, and the teleportation target is confirmed as soon as this function returns true. And speed is a function providing the speed for gradual teleportation. Notice that custom functions roughly match the breakdown for the different configurable options. Alternative factorizations exist. For example, we could require the user to provide a single target vector3 function regarding the selected target, instead of asking separately for the target selection subtasks. Our factorization, though, provides multiple advantages. On the one hand, it is close to that of the user interface adjustable options, and thus easier to understand and remember. On the other hand, the proposed factorization facilitates code reusability and simplifies development since empty custom functions take the default behavior. For example, the experimenter might choose to provide a custom function just for the pointing direction while reusing the default behavior for the rest. Let me now discuss a pair of use cases that benefit from fast iteration cycles for optimizing navigation. The first case is a medieval church with mural paintings. The goal was to provide intuitive navigation for art historians to explore the mural paintings of Sant Quirze de Pedret using a standalone VR headset. The designer used Google Chrome running on a desktop PC for testing different navigation techniques and an Oculus Quest for fine-tuning. While using the desktop PC, we used the WebXR API emulator. The tool allows us to quickly discard continuous steering techniques due to motion sickness issues. We tested large field of view reduction, but this prevented users from seeing the mural paintings above the line of sight, for example of the apses. So we found field of view reduction not appropriate during a steering-based navigation. We thus opted to default to a free teleportation technique using the handheld controllers for selecting the target position. Parameters such as maximum distance and gradual teleportation speed were also fine-tuned to the reduced size of the charge. In our second use case example, our goal is to let art historians to inspect Sant Quirze de Pedret surroundings and architecture, this time emphasizing on the outdoor model. Free teleportation was tricky because the church is on the edge of a long and jagged hill mountain at the foot of the Pyrenees. On the other hand, the scan locations were readily available, so we decided to test and fine-tune teleportation using as predefined targets the scan locations, which also guarantee high-quality viewpoints of the model. In conclusion, we have discussed the benefits of a web-based tool for quickly designing, testing, and comparing navigation techniques for virtual environments. Our hypothesis is that if testing iteration cycles are very short, designers can fine-tune the default parameters of the chosen navigation technique to the specificity of the 3D environment, the user task, the target users, and other contextual issues. Our tool supports the design of inclusive VR experiences in the sense that fast testing allows designers to offer a catalog of preset navigation techniques to cover the largest possible audience, and because the user interface allows end users to further customize navigation options to suit their needs. As future work, our first priority is to further evaluate the usability of our framework. We want to evaluate if the development of custom functions is fast and suitable for developers. We also wish to add further high-level methods to facilitate writing such functions with a few lines of JavaScript code, including, for example, filters to smooth out user input. So that's it. Thanks for your attention.
Thank you very much. Let's see if are there questions from the audience. A very, very interesting presentation. It's quite very, very interesting for me because we are actually researching on this topic on navigation in virtual reality in our lab, and we are setting up some experiments on reduction of motion sickness during navigation. So it seems a very, very useful tool. So
I can see a question from Fabio.
Okay, sorry.
Yes, so Fabio is asking if, do you think in the future the navigation metaphor is going to be separated from the rest of the application? It seems to make a lot of sense. I completely agree. So I think that the navigation part, ideally the navigation part should be completely customizable by the user. Even for non Web3D applications, for conventional viewer tools, it would be nice that people have some kind of plugin or some extension mechanism so that people can really customize the navigation, even, for example, thinking on the inclusion for people with disabilities, for example, the ability to define their custom mapping as much as possible. And in the case of Web3D, the JavaScript and of course 3GS and all the typical tools that we use allow for the runtime evaluation of this, so it's easy to separate relatively easy to separate the navigation metaphor from the rest of the features of the application. So yeah, it would be very nice. Sometimes I use some 3D applications that excel in some, for example, processing features, but the navigation part, maybe it's been optimized, for example, for some kind of scenes or for some kind of users or devices, and it's a pity because this poses an entry barrier for some users. So yeah, I completely agree with Fabio's remark.
Yes, but I assume that your technique is ready for this. You are changing the navigation control at runtime.
Yeah. That's so. I was referring that it would be nice if all the applications, for example, Sketchfab has very interesting navigation metaphors, but there is barely no options for the end users to customize it. And that's a pity. So I was positioning myself on the importance of the navigation part of any 3D application. So
do you think that there could be, in principle, problems, conflicts for? I mean, in some application, I think that there are constraints to the navigation that may conflict with the settings of the navigation control you have.
Yeah, well, in our current prototype, we haven't extensively tested any type of a scene. And so, for example, in the case of teleportation, you cannot just take any scene and use teleportation, because usually you have to define the virtual floor, so the walkable space where which let's say horizontal surfaces can be a potential target for teleportation. You can try to do this automatically, but usually, at least in games, it's a subset of the surfaces which is very well designed. So it's not. It's true that there are some constraints, but I think that we should try to. It would be very nice if navigation is also part of future standards. Even for non-VR navigation, we sometimes conduct user studies, and so for people with no 3D experience, usually not for when inspecting single objects, but when going, for example, from one room to another room inside a building, usually the hardest part is the navigation. And even for people with 3D experience, if they are used, for example, on Blender navigation, let's say, and then simply the metaphor implements, for example, mouse movement, the opposite as what they are used, they find it difficult to move through the scene.
Okay, thanks. There is another question.
Fabio says, in the video games domain, the ability to customize would be part of the gamer's skills. For example, in the Oculus Quest games, I have more experience with. Some games really, the developers put a lot of efforts in allowing users to customize every single aspect, but there are just a few games that really offer this possibility. But even in these games, they are not as inclusive as they could be. And the next question, what physiological sensors exist that a user can wear to feedback to algorithms that dial back or alter the navigation mode to prevent motion sickness? How fast is on set the motion sickness, and are there common indicators that wearable sensors can detect and correct to navigation settings and trajectories? Wow, that's that's a good question. Let me read it for the rest of the audience. So the first part of the question is, what physiological sensors is it that a user can wear to feedback to algorithms that dial back or alter the navigation mode to prevent motion sickness? I'm not an expert on this topic. Some studies show that sometimes motion sickness starts minutes or even hours the VR experience. So sometimes there is a variable lag, user-dependent lag, between the motion sickness symptoms and the actual discrepancy of visual and vestibular stimuli. So because of this time between the onset of the symptoms and the actual VR experience, I'm not sure if really there are opportunities for sensors to capture, to monitor or to track the motion sickness of the user in order to modify the application. As much as I know, okay. How fast is the onset of? Okay. So how fast is the onset of motion sickness? Okay. So as I said, I am aware of some studies that say that sometimes, depending on the users, the onset is quite slow. Okay, and even sometimes people start feeling dizzy minutes or even hours after the VR experience. Okay, so it would be very nice if we find some kind of signature or something that we can detect. Maybe I don't know, eye saccades or something like this, or some behavior of the user, but I think it's at least I'm not aware of any techniques on this direction.
Thank you. I'm not aware too. We have we are actually doing some research, performing user studies on motion sickness, and I read some literature on this, and actually the most common way to detect and measure sickness for assessing the effectiveness of different methods like field of view restriction and so on in the literature is using questionnaires, because there are standardized questionnaires for doing this. And we tried to use some physiological sensors like galvanic skin response sensor or something with bad results. I think someone uses postural sensors, but there is not a method that is able to detect sickness in a reliable way.
There's another question. I will say that there are situations where the navigation method has been explicitly chosen to obtain some effect. It might be part of the narrative. So on one side, it may make some sense to override the standard navigation with my own. In some other cases, it will be disruptive. Yes, I also agree. One example is horror VR games. Because usually the default behavior in these games is that you navigate in the direction of your head, so that if you look at the monster, let's say, that is hunting you, then you are advancing towards the enemy. Okay, so that's sometimes it's part of the narrative. I completely agree.
Okay, thank you again. I think we can move to that. I have just one very quick question to end. Is your tool available for other researcher, or is private?
There is initial version in a GitHub repository, but we are making it more reusable. So before Christmas, we will post in our webpage the new repo with more full-fledged code.
Okay, thank you very much. I think we can skip to the next and last paper of the session, that is sharing ambient objects using real-time point cloud streaming in web-based XR remote collaboration by Yonghye Lee, Gyun Yo, and Sohong Lee from Korea. And please, you can start the video presentation.
Hello everyone, I'm glad to present our work at this WEB3D conference. This is Yonghye Lee, and today's topic is sharing ambient objects using real-time point cloud streaming in web-based XR remote collaboration. I'm a research assistant at the Korea Institute of Science and Technology and have been studying web-based XR collaboration methodology since 2016. Our topic is covered by this sequence: motivation, previous works, our approach, implementation, and conclusion. Recent advancement in hardware and vision technology has made extended reality become more practical and more popular. Probably one of the most actively used XR applications is remote collaboration. This is because it allows more intuitive information delivery by displaying visual information instead of using speech or writing. Moreover, in remote collaboration, it is important for a user in a local site not only to receive information from others, but also to give them information about the local environment. To accomplish this, a variety of methods to share a local environment with remote users have been suggested, such as video sharing or mirrored 3D world. However, these methods have some drawbacks. Information drawn on display is sometimes too abstract to understand. Besides, a complicated hardware configuration is required to imitate the real world, or a lot of advanced preparation is required to make 3D resources before the collaboration. Our proposal is built on XR collaboration system, where users can share their environment in rich information and on the spot. Next is previous works. In the last WEB3D conference, we had introduced unified representation for XR content and its rendering method. In there, we devised special HTML tags that is representing the XR entities, which are called the WebXR tags, in short WXR tags. Authors can make an XR content by compositing these tags, and the content can be run on both AR and VR devices without any specific modification of the content. This cross-device execution is accomplished by a special XR renderer, which is called the WXR renderer. This renderer chooses a distinctive rendering strategy according to the currently selected XR mode by users. Consequently, with the WXR tags and the WXR renderer, people can literally create and consume XR content through the web. In addition to that, we have devised the concept of the unified coordinate system, which is a method to locate the pose of an AR camera in the VR coordinate system. In there, we introduced a special marker called the space marker. Serving as an indication for a static point in an AR space, the space marker enables distinguishing the movement between an AR camera and other normal AR markers. This method ensures that users robustly find the AR user's location. Even camera tracking systems such as SLAM or visual odometry don't work. This idea is included in the published research paper, XR Collaboration Beyond Virtual Reality Work in the Real World. Sharing local environments helps remote users to understand the context of the local site. There are several ways to attain this. One of those is using a live streaming. In this method, a local user takes and sends live video of their environment by using an AR camera, and remote users watch this video in VR. This method allows that the local user directly shows their environment to remote users. However, the weakness of this method is that the remote users cannot interact with the environment. They only can point or direct the way to an object in the environment. Another way to share the local environment is making a replica of the local environment before collaboration begins. In this method, remote users dive into VR and interact with the virtually copied local environment. One drawback of this method is that the pre-constructed 3D model does not reflect changes of objects in the local environment once after they are made. Thus, systems adopting this method are only available when both local and remote users work on virtual things, not physical ones in the local. Some research exploits these aforementioned methods to complement the drawbacks of each method. In remote collaboration, real-time data exchange is essential. WebRTC is an effective means to build a reliable, expandable, and low-latency service on the web. Already in the market, commercial products using the WebRTC have been heavily emerging. Next is our approach. We propose a system that enables local users to share their local environment with remote users in real time. This system is based on the web-based XR collaboration system, which is introduced in our previous works. This previous work enables collaborative users intuitively communicate through XR entities of their working targets. However, in this previous system, no way of impromptu sharing local users' surrounding environment is served, so resources representing the local environment should be prepared in advance, like as VR background videos or images or pre-constructed 3D models. Thus here, we add functions sharing a local user's environment to the previous system. Firstly, we conceptualize the world by two things. Those are the object of interest and the ambient object. The object of interest, shortly OOI, is a target that users work on, and the ambient object, shortly AO, is an object except for the OOI. Additionally, we assumed that OOI have frequent movement and that AOs are always static. This assumption is valid particularly in collaboration, because fixing something always entails a physical adjustment of its state and other things remain unmoved, since it is our collaboration objective. Defining this concept, we can easily figure out which object should be shared as a collaboration target or which object should be shared as a local user's environment. The environment sharing process is divided into 3 stages. The first stage is point cloud reconstruction. In this stage, we use a LiDAR sensor to gather depth information of the local site, then restore the 3D position of the depth point. The next stage is filtering out obstructive points from the point cloud. The final stage is splitting the point cloud into a couple of fragments and sending them to other users by the RTC. For sharing local users' environment, we choose point cloud as the medium, rather than 360 image, because in 360 image background, the users cannot reach the ambient environment object. This video illustrates this limitation. The left side shows a remote user experiencing a 360 image and the right side shows him experiencing a point cloud for the same local environment. We can check that the glass wall, window, and chair in the background are still in the distance, even though the user is moving forward. In addition, it looks that the virtual environment comes to the user when he moves forward. Conversely, on the right side, every object becomes closer or farther relative to his movement. Furthermore, it seems that the virtual object is floating in the air in 360 image background. Contrarily, the model looks light upon the table in the point cloud background. The point cloud reconstruction process is quite simple. We recovered 3D positions of points from a LiDAR depth map by using the pinhole camera model and a triangle resemblance. Before the point cloud, which we got just ago, is joined to the entire point cloud, we should remove points that disturb the virtual environment. These points are generated from the surface of OI and screen the 3D model of OI, making it difficult for the users to recognize the model. This 3D model should be recognizable for remote users to give instructions to the local user, but it is quite difficult because the model is obscured by the points. Moreover, if the OI moves, the points remain after images and consequently mess up the virtual space. Because the OI is the target to work on, its movement frequently occurs. Thus, these after images are inevitable, and so we should mask out this point. The masking process is detailed here. By the unified coordinate system, a virtual camera's pose aligns with the physical camera's pose, and to augment a 3D model of an OI, the field of view of the virtual camera is matched with the field of view of the physical camera. Considering these things, it can be seen that the appearance of the OI reflected on the physical camera and the virtual camera is identical. From this fact, we can remove the points representing the OI by checking if the points are within the OI's area in the screen space. The check is proceeded using the depth buffer of the 3D model render. The depth buffer is also known as G-buffer, and each value in the buffer is called G-value. We define here the range of G-value as 0 to 1 inclusively, and the default of G-value as 1. Note that although we theoretically define the range and default of G-value here, these are also the same as the value defined in the graphic libraries such as OpenGL and Direct3D. When we look at the pixel at the lower right corner in the rendering image of a 3D model, it has the G-value as 1 because the pixel is outside of the OI. So we can determine that those points which are rendered at the pixel are not representing the OI. However, in the case of the pixel at the center of the rendering image, that pixel's G-value is 0.999 approximately. Thus, we can determine that those points which are rendered at the pixel are representing the OI. Based on this determination, we just discard those points. This determination is conducted for all pixels in the rendering image and repeated on each frame of point cloud reconstruction. As a result, we can obtain a clean point cloud accepting the points representing OI. Moreover, because the point cloud reconstruction is still working, as the OI is moved, At the same time, new points are formed at the newly revealed areas. You can find the information in the right video. As the cyan flange model moves to its left, the hole on the desk is filled with the newly generated points. Note that this masking process is very efficient because it proceeds at the fragment shader level rather than the vertex shader level. In the last stage, the masked point cloud is sent to remote users through the data channel of WEB3D. For practical reasons, this channel has limited data capacity that can be sent at once. Thus, we should divide the point cloud into a couple of massive packets. Before dividing, what we need to know is that color and vertex purpose are separately managed for the purpose of efficient memory access. If these points are sent in the sequence stored in the memory, packets containing color information and packets containing position information depend on each other. Because the points are rendered not until both color and position information are available, a delay happens until a dependent is arriving. This issue can be resolved by reordering the data. By interweaving the color information and position information of the points in one packet, it is possible to prevent dependence from occurring. As a result, the remote side renderer can draw the points as soon as they arrive. I will then move on to prototype implementation. As I mentioned, the proposed system is based on our previous study, so the architecture is similar at some level. The mainly improved part is those related to the environment sharing feature. The AR engine module on the local user side tracks OIs and scans the local environment with LiDAR. In our implementation, we use the AR kit here. The generated depth map from the AR engine module is passed to the point cloud generator module to process it into reconstructed point cloud. The OI masking stage is also conducted in this module. Then, the masked point cloud is passed to the point cloud streamer module, in which the point cloud is split into pieces of a message and delivered to remote users. This video demonstrates our implementation. The upper left shows a remote user and the lower left shows a local user, and the right side shows a third-person view of the user's collaboration. In this collaboration, their task is disassembling the ball valve, which is in the center of the local site. This means that the OI is the ball valve and the AO is the surrounding of the local user. Before starting the collaboration, the local user looks and scans around briefly. By doing this, the remote user can understand the local user's context. Note that due to the OI masking, a hole is made under the OI. Later the OI is moved. In this case, the ball valve handle is rotated. This hole is exposed to the LiDAR and filled with the new point. And also we can see the remote user recognize the existence of the scanner in the local site and entice the local user to use it. In conclusion, in this presentation, we propose a new concept that distinguishes object of interest from ambient objects in XR collaboration, and filtering out the points representing OI from reconstructed point cloud using 3D model of OI, and an efficient data structure for transmitting point cloud under WEB3D communication. In the future, we further do conduct a quantitative user survey to verify the efficiency of using the suggested XR collaboration method. This was Yongjeri from KIST, and I appreciate your listening. Thank you.
Okay, thank you very much. Are there questions for this presentation? Okay, I just I wanted to ask about if you planned user test, and you partially answered now. But I was wondering which are the practical scenarios of use that you are going to test with these user tests. Can you tell us something?
Actually, actually this time we are trying to excavate the real scenario for using this system. One thing is the user, the local user has any device to capture his or her surrounding environment. So in there, he can use this system for capturing the point cloud or 3D world of the surrounding environment on the spot. So remote user who doesn't existent in the local site can experience the local site in real world.
Sorry.
Is your answer?
Yes, sorry. Is there the question? Yes, I think.
Open this conditions like this.
Yes, it's about bandwidth.
Or is a higher bandwidth always necessary for detailed collaboration? Yeah, in our system, for the Boltzmann's, for the Dawn's question, in our system, it is necessary using the high bandwidth for streaming the point cloud. But after sufficient points are shared, then the local user can decide to don't using the sharing mode.
So you don't need in this way high bandwidth. So because all the point cloud is shared at the beginning.
Pardon me?
So you don't actually need high bandwidth in the practical application.
Did you mean the high bandwidth is required? Sorry. I can understand what you're saying. Sorry.
So the collaborative part doesn't involve transmission of a high amount of data, right?
Yeah. You're right. The collaborative part is just is synchronized by just sharing the position data of 3D model.
Okay.
So is conducted by in the low bandwidth.
Okay, thank you. Any other question? Okay, if not, I think we can close the session, and thanks to all the presenters and all the attendees doing questions. And I think that we can have a break, and you can stop the session.
Okay.
Thank you very much.
Thank you a lot, Andrea, for being here today. I know you have to run to catch a train, so thank you again.
To go to teach. So
we will we'll meet again in 12 minutes at 11 for the social event. So be there, be ready, and talk to you soon.
Bye bye.
Thank you very much. Bye.
Bye.